All right, so yesterday we left off talking about the blade has a path through the air like a corkscrew or a regular screw. Let's see, I think I have another slide of that. There we go. Distance moved in one rotation, low pitch versus a high pitch. So we were talking about why would you even want something that has a low pitch to it? If every revolution that this propeller down here goes around, moves the airplane forward more, why would we not just want this all the time? Well, one of the problems with a high pitch is that it takes more power to move it. And if you put a prop on an engine that has, say, a fixed pitch, and it has too much of a pitch to it, and you put it on the engine, and you do a static RPM check, you can have high or low RPM? Low RPM. If you have low RPM, does that mean you have, what's that going to do to your horsepower? Decrease. Remember Planck. So that's one of the things. So if you put this on, you're going to then not have enough horsepower. It's kind of like starting, if your car has, geez, some have 7, 8, 9 gears now, but say you have 5 gears in your car. Well, why would you use 1, 2, 3, and 4? Why not just use 5? The engine doesn't have enough power, so you start out at 1. So same thing. We'll talk about constant speed props in a few weeks, which is like shifting gears, but not quite. All right, so the last thing we said, which will be the first thing we say now, sorry about that, is the blade has a path. The blade has a path through the air like a corkscrew or a regular screw, if you like. So the amount of bite that the blade takes is determined by the blade angle. So you have a high pitch, which would be a big bite, or low pitch would be equal a smaller bite. So the amount of bite, speaking of bite, it's crunching away over there. Amount of bite the blade takes is determined by the blade angle. So if we have high pitch or high blade angle, it's a big bite. So is the airplane going to go further per revolution or not as far per revolution? Further, okay. And then low pitch or low blade angle equals a smaller bite. All right, then we talked about pitch distribution, right? What is that?
The change of the shape of the...
There we go. Change of the blade, the twist of the blade. And each segment is a little different because of the way the prop is going to interact with the air. Let me see, skipping some stuff here. Blade angle has a pronounced effect on the mass of air moved. As well as engine RPM. So what I'm saying is a little bit of blade change, a little bit of angle makes a big difference. 1 degree of blade angle change can change engine RPM by 60 to 90 RPM. Change engine RPM by 60 to 90 RPM. So what I'm talking about is like static RPM. Everybody follow me when I say static RPM? That means a fixed pitch prop on the ground, not moving, because it's just an easy way as a mechanic to judge horsepower of the engine. So if I have a prop and I go out and I check the static RPM and I get 2300, if I put 1 degree of pitch, take it off, have it repitch, put 1 degree more pitch in the propeller, I'm going to lose 60 to 90 RPM. And the range on type certificate data sheets isn't a real big range, so you could actually knock it right out of airworthy. Yep.
So you are making the engine do more work to make the propeller go through the air?
Well, a lot of things happen. Yes. So the engine has to work harder if it's taking a bigger bite. So if you take too big of a bite and the engine has to work too hard, it's going to pull the RPM down. Pull the RPM down, then you've lost horsepower. You lose horsepower, you can't climb. So it's just this vicious little thing going on there. So you've got to have a propeller that's designed for the right RPM range. And if you don't, then it's not going to work out well.
So 1 degree of high pitch, you lose 60, 90?
Yep.
1 degree of low pitch, you gain 60, 90?
Yep.
Okay.
It goes the other way too.
Could you say that you also have then more torque on the crankshaft
With which,
with higher angle, higher pitch, because you're pushing more air back, so you're
yes, but you're losing horsepower, and horsepower is a function of torque. So if you lose the horsepower, then you lose the torque.
probably not.
But if all things are equal, then yes. Let's see. Reason why blades have pitch distribution in many different airfoils, because the blades move in multiple dimensions. It's a lot to write, but I think we'll do that. The reason why props have pitch distribution pitch distribution, twist, and many different airfoils is because the blades move in multiple dimensions. So what do I mean by that? Well, let's see. Multiple dimensions. First of all, we have different rotational speeds at each station. How are stations defined? Inches from the hub. Okay, so different rotational speeds. I don't mean RPM. I mean actual like miles per hour speed. So near the hub, is it faster or slower?
Slower.
Okay, tip is then?
Faster.
Okay. So first of all, we have that going on. Then forward movement. Of the aircraft creates different angles of attack for each station. Different angle of attack for each station. And what is angle of attack?
The angle in which the air hits the airfoil.
All right, angle of attack is angle between? Okay. Angle between chord line and, say it, Steve? Relative wind. And by relative wind, we don't mean Uncle Jerry's. Never mind. All right. Let's do this one then. 1, 2, 3. Example. of y. Each station is different. Oops. Different. One, the ideal angle of attack on a blade is, anyone want to guess?
2 to 4.
Thank you, 2 to 4 degrees. 15 degrees will usually result in a stall. And blade angle is smallest at tip and largest at hub. Yo!
Does the airspeed of the airplane increases? Does the angle of attack increase or decrease?
I'm going to show you that in just a second. So it's a very good segue. Thank you for bringing that up. I'm glad you asked. Let's see. We will go here. And we will go here. All right, we looked at this one. All right, this can be a little confusing. So let me make sure I go through it correctly the first time. This is an example of an aircraft at 150 miles per hour at 2,000 RPM, if I got this right. Using Pythagorean's theorem, everybody remember what Pythagorean's theorem is? A squared plus b squared c squared. And that is used to determine, well, you can determine the hypotenuse here, which is the angle. So we're looking at this. Number A shows a blade at station 36. So we're looking at blade station 36. What does that mean?
36 inches.
Okay, 36 inches from the hub. And in this particular case, for every 1 foot, the plane moves forward, the prop at station 36 rotates 2.9 feet. Everybody follow that? So for every 1 foot the airplane moves forward, that prop moves forward 2.9 feet. If we figure 2.9 feet and we have 1 foot there, then we can figure out what the distance is here. Doing that, we can figure out the angle, which means that this should be at the relative wind hits the blade at an angle of 19 degrees. If it does in fact hit the blade at an angle of 19 degrees, what should my angle on the blade be? Well, that would be an angle of attack of 0, so that's not good. So I want an angle of attack of how much?
2 to 4.
2 to 4 degrees. We'll shoot for 2. How about shooting for 2? So the angle of this blade should be,
21.
okay, 21 degrees. Or we can hit the middle, 22. So the blade angle must be 22 degrees. We'll go for 3. So it'll be 22 for 3. How's that sound? So if I want to shoot for 3 degrees difference between the relative wind at 22. Yeah.
Is the 2.9 feet the geometric pitch and the 1 feet?
No, it's how far it literally moved.
Oh, so like
Yeah,
if
how far
you
it
move
travels.
2.9 feet?
The airplane moved forward 1 feet, so if you take the distance that it actually moved, it's 2.9 feet.
Oh.
So it's a section of your geometric pitch, so to say.
Yes.
Where did the 19 degrees come from?
All right, where do the 19 degrees come from? If the prop moved 2.9 feet, and we plot that out, 2.9 feet, and the airplane moved 1 foot, and I plot that out 1 foot, and I use Pythagorean's theorem, a squared plus b squared equals c squared. This is a, this is b, and this is c. All right, so we can do that and come up with a distance here, which I don't happen to have, and I don't want to do it right now. But we come up with that distance. Then do you remember back in electricity when we did this, and we used SOHCAHTOA, and we figured out the angle based on that using sine, or arctangent and all that. Okay, same thing. So we just figure out Pythagorean's theorem, arctangents, and you come up with 19 degrees. Is this angle right there? So that means that relative wind is hitting the blade at 19 degrees. Got it? So the relative wind is coming at the blade. So here's my blade coming through the air. It's coming at 19 degrees through my blade. Follow? All right. So if the blade is flat, that's going to be bad. I need to figure out what that blade should be at. And so what angle would be a good angle for that blade? If it should be 2 to 4, 3 is perfect then. We'll say 3 is perfect. Then what should the angle of the blade be? 22. Okay, so somebody figured that out. At station 36, I don't think I have it written down here, but that's a station 36. The blade should be at 36. At station 36, the blade angle should be 22 degrees. Follow? Mm-hmm. All right, but that's only at station 36. Now, if I want to do something, let me see here. We'll do station 24. So at station 24, same prop, same everything else. The aircraft moved 1 foot forward. Nothing's changed because it's attached to the, yes.
Is the station number given on your, for this somewhere else, or are you making up the station?
It's given somewhere else. So, don't be difficult. Sorry. Okay, so let me see. So, where are we? B, this is, and that's why I said this is an example, and I told you earlier, it's 150 miles per hour. It's given somewhere else at 2,000 RPM for this particular plane. All right, so now we're going to look at B right here. So we're at station 24. Again, the airplane moved forward how far?
1 foot.
Right, because it's attached to the same propeller, moved 1 foot. But this time we're looking at station 24. Is that further in or further out?
Further in.
Okay, it's further in, so it didn't move as far. Right? So during that revolution, it only moved 1.94 feet. So again, using Pythagorean's theorem, you can figure out this. You can figure out the distance here, which you can then figure out the angle that comes out. And they did it for me, and it just happens to be 27. So what should the angle right here be on this particular station at 24?
30.
All right, 30 degrees. So we had 22 over here. Now we had 30 right there. So we can see how we're getting the twist in the blade and why we're getting the twist in the blade, right? All right, so last one, station 12. Very close to the hub. How close to the center?
About a foot.
Would you say about a foot?
It is exactly a foot.
Right about a foot. In fact, so close.
Nominally a foot.
Nominally a foot. All right, so the airplane's going to move forward how far? 1 foot. This time, out here at station 36, the prop went 2.9 feet. Now all the way near the hub, it's only going to go 0.97. So it's moving not even as far as the airplane's going forward. So again, using this there, and we figure out the angle, which somebody did for me. They come up with the 46. So what should the angle of the blade be near the hub? 49 degrees. Look at you guys. Got it all figured out. And you know what? It matches my notes. So there we go. So that explains why this particular prop, in this scenario, why you have to have pitch distribution. So what would happen if, let's just say, we picked something in the middle. I said, well, what the heck? Station 36, 22 degrees. We'll just make this 22, and we'll just make this 22. Is it going to work?
No.
Not very well, because we have a difference of 7. I'm sorry. Try to do some math. 5 degrees. Would it be okay?
Not stalling it.
It's not stalling. Better than a piece of flat plywood, I suppose. But how about we get down here? Is this any good?
No.
Down on C? No, it's stalled, right?
Mm-hmm.
No good. So there we go. That wasn't so bad. Let me see. Kind of the same thing here, just shown in a different format. Okay, we'll get to this one. Let's go back up.
just explain one more time about the stalling of the blade of the propeller?
Okay. Just like a wing. I'll keep it for now. Well, that didn't work. Go back here. Just like a wing, if we don't have the air coming at the wing properly, I think we need blue for wind. If we don't have the air coming at, if it's a wing, in the proper orientation, then it's not going to work. See what happens if we get air coming around this way, where it's too steep, it can't make, we got to do it this way. So we got our wing. So as the air, nope. Oh, look at that. I'm learning all kinds of bad things here. Okay. So as the air is coming along the wing, you want it to kind of split and go over, right? And let's go this way, down, that way. Okay, so you want it to do that. And that's good. What is bad is if we rotate the wing or the air is coming at it from a different angle. So if the air was coming at it from this way, then it kind of bounces off and goes that way a little bit. But it tries to make the turn here, and it just can't, and it just kind of falls off like that. And so you can get a lot of turbulence back here, and it's not sticking to the wing. So when it does that, it's going to stall, right? And so it's no good. We don't have Bernoulli's principle happening up here at all. We just have yuck. That's a technical term. So we just have that garbage going on. And so it's not a wing anymore. It's not working. So it's the exact same thing with the propeller.
Is there a certain degree in which the propeller stalls?
Yes.
Why did you add 3 degrees each one, not 2 or 4?
Because 3 is in the middle.
Okay.
It's 2 to 4. So I could pick 2. I could pick 4. What's right between 2 and 4?
I'm going to go with 3.
You're going to go with 3 on that one?
3.
All right.
That's why you picked it then? It's not like it. Okay.
Yeah, just pick 3.
What was the reason?
No, in the middle. Could have picked 2, could have picked 4, pick 3. 15 degrees was the answer to your question. We usually result in a stall. All right, so let's see. I'm going to get rid of that right there because we kind of covered that. 4 was all my example, and so was 5. Let me see. Well, I guess that was stupid. All right, so we'll just put 4 again because I'm going to keep going. Angle, see the angle of attack. The angle of attack will change with any change in, can you guess? RPM or
velocity.
okay, or forward velocity. I'll put aircraft speed, so I don't have to spell forward and or velocity. Now, if we think that through just a little bit more, you were going to design a fixed pitch propeller. Okay, now we go back to Orville and Wilbur Wright, who had to design a propeller for their aircraft. Where do you even begin? What angle do you want?
Depends.
Well, first of all, what do you have to figure out?
How fast do you want it to go?
How fast is your plane going to be going? And
Your engine.
what RPM you're going to spin at. And if either one of those are off by just a little bit, then your propeller is inefficient. Well, now let's think about just a fixed pitch propeller on a little 150. You start out at how many miles per hour?
0.
Good guess, 0. And you go all the way up to the maximum velocity of,
75 miles an hour.
you're being generous, but no.
If you're going down.
Yeah,
With the tail one.
yeah.
105.
About 90 miles per hour on a good day. Really good day.
With
All right.
80 mile an hour downwind.
So well, then it doesn't count because that's ground speed. All right, so you have to design it for this entire range. So where is it going to work best? Well, certainly 0 wouldn't be good, or 2 or 3, so you're going to pick that spot where it's going to work best. But then you start thinking things through, and all right, so you figure, all right, so let's just say, cruising RPM is going to be 75% power which is what?
Cruise.
It is. I just said that cruise is 75%. So
75%
what?
of red line-ish.
But it's not 75% of red line. That's the funny thing. So if you look at a chart in the pilot operating handbook, it will tell you that if you are at 1,000 feet, then it's going to be 2,450. And if red line is like 2,700, well, up at 5, 6, 7, 8,000 feet, what's 75% power? Wide open. It's red line. So yeah, it's red line RPM, but it's not red line power. So you have to look at a power curve. So you go up in altitude, you're going to spin the engine faster. Hopefully you go a little faster. The two things equal out, but everything changes. Yeah. So fixed pitch props are typically designed for optimum efficiency at a narrow set of parameters. It's not that they want that. Shoot, I would love to have a propeller that was optimally efficient at all speeds and all RPMs, but it doesn't work that way. So, and what is the ideal angle of attack?
2 to 4 degrees.
All right, so I don't have to write that again. All right. Let's look at an example of angle of attack when stationary
This here.
versus in flight. All right, so here we go. On the ground, propeller moves from point A to point B because I'm on the ground and I'm not moving. So it's just going to, stop it. So it's just going to go through this plane of rotation. And where is the direction of relative wind?
Straight down.
Straight down.
Or straight up. So right here, relative wind is just coming like that. So what is my angle right here? Or as they have it, C.
45.
That's a big angle. You think it's being efficient?
No.
All right. So angle of attack here is very inefficient. No good. NG. All right. But we start rolling forward. So let's think about it here. So if I'm going to check, again, static RPM is something that we do as mechanics. We check the static RPM. So brakes on, full power, and we see where the RPM is going to go. Now, if it's a fixed pitch propeller or ground adjustable, you can do that. If it's a constant speed propeller, it's usually designed to let you go right up to red line because the pitch is going to change. And say, oh, you want to go to red line? Well, let's go. And so the pitch will change and allow you. But we're talking about fixed stuff right now. So as I'm sitting there, I'm going to have this very high angle of attack, which is going to be inefficient, which is really going to kind of want to bog the engine down, right? So you're not going to get anywhere near red line. Now I take my feet off the brakes and start rolling forward. What's going to happen to my angle of attack?
It's gonna shift
Towards
towards
better.
It's going to shift. It's going to start coming up. And the faster I go, the more it's going to start coming around to the front, decreasing that angle until it starts getting very efficient. Now it starts getting efficient, it's going to work better. And what do you think my RPM is going to do too? Increase. You start seeing that increase of RPM as you start rolling. So,
changing because the relative wind is changing?
yes, it's only changing because the relative, well, you're going to increase RPM too. Again, everything always changes. RPM is going to go up, but more importantly, your forward roll is going to go. You're going to get forward rolls, so that's going to increase. So that's going to really have a change of the direction of the relative wind, which is going to bring your angle of attack hopefully into the proper area. So this is kind of the same thing, just showing an evolution. So no forward motion, some, and a lot. So it gets better. So if somebody asks you that question, What happens to the engine RPM as the aircraft starts to roll? Your answer would be? And you would know why. So if a customer came to you and says, I got a problem. It's a terrible problem. And my friend doesn't have this problem with their airplane, but I can see that my red line is at 2,700 RPM. And whenever I'm sitting there with my feet on the brakes and I go all the way to red line, it only goes to like 2,300 RPM. And you say, well, what happens when you let your feet off the brakes? I'm glad you asked that. And they're going to say what? It goes up a lot. Must be because of the ram effect of the air coming into the carburetor, I would guess. Is that true? No. Not necessarily, no. It's because you're better angle of attack. And so armed with that information, and they say, well, what is the RPM? They could tell you, and you could actually look it up on what? Where would you look this up? Type certificate data sheet would tell you the thank you, the static RPM, and then you'd know if they're right or wrong. So yes, Alexander.
How the relative wind is changing with forward motion.
Sort of a conceptual thing, because the propeller, if it's just sitting here going down, the air is kind of coming at it like this, right? Well, let's see if we're doing this right. So it's kind of hitting it like that. Yeah? Okay, that's not good. But as I start to go forward, doesn't it kind of change? So instead of being right here, as I go forward, aren't I getting air going this way?
You're kind of gliding it off.
I'm going to say gliding it off of that.
You're moving it out of the way.
No, the airplane's going forward. So you've got, I don't want to keep doing the same thing.
Run really fast.
Huh?
Run really fast.
You try it. You run really fast. But you just have to realize if I'm sitting here and there's no wind anywhere, and the prop is going this way, where the relative wind is hitting it straight up and down. But if I start to run down the hallway, doesn't the wind, instead of being straight this way, doesn't it start to kind of rotate towards me?
It's like almost like air being like a fluid, I guess, in a sense, right?
It is, yes.
Yeah, because you have fluid sitting around you and you're just chopping at it. It's not moving, but
Right.
as you're moving through water or something, then and your prop's going, it changes the. That's the only way I can really think of it.
Well, that works.
Right.
That's exactly true. So it's just the forward speed changes the angle, or the air that's coming at you, and then it just changes. So tomorrow what we can do is we can run up and down the thing, you and I. Well, you run. I'll just bring a lawn chair. Well, let's have you do it until you say you get it. I get it. No. All right, so we did an example of angle of attack when stationary versus in flight. Let's see. There's a lot of stuff there. And then we can get into climb or dives, which is really going to change things, but I think I'm just going to make things a little more difficult if I get too in depth here. So let's talk about pitch. So pitch is often used in the same term as blade angle, but it's not quite correct. So pitch is often used as a synonym for blade angle, but that is not correct. So what is blade angle? Didn't we already define that?
Angle between the chord and the plane of rotation.
Between the chord and plane of rotation. Very good. So that is blade angle. Pitch is the distance the aircraft will move, I'll say forward, with 1 revolution. So you can see why it's used a little synonymous, because we say, well, it's got a high pitch. Well, it's the same thing as saying it has a high blade angle. So that's kind of okay. But technically speaking, blade angle is an actual angle and pitch is a distance. So if I say, hey, what's the pitch on that prop? You should not come back with a degree. Well, the pitch is 20 degrees. No, the pitch isn't 20 degrees. What's 20 degrees? Blade angle. All right. And if I said, well, what's the angle? You shouldn't say, well, the angle is 4 feet. All right, that wouldn't work. So let me see, we got that. Pitch. We'll put this one. B, pitch. Refers to how far the aircraft, well, it's being redundant, will move forward in 1 rev based on the blade angle at the 75% station. So it's just taken at that spot. Why? Just because somebody decided, an engineer, that that's where we should do it. I don't actually know, but that's like the average spot is at that 75% station, and that's where everything is taken from. So let's talk about this. We have 2 different terms: geometric pitch. And the geometrical pitch is the theoretical distance. So in a perfect world, that's exactly how far it would go. So the theoretical distance. Theoretical distance, an element of a prop would move forward in 1 revolution if it were moving along a helix having an equal angle to the blade angle. Linear and measured in inches. And let's see, should we do this? I don't know. Geometric pitch is equal to 2 pi times r times tangent of blade angle. And rather than go through this big long example, I know that you can do it in lab, and so I think we'll do it there. Or should I do it now?
Let's say tangent.
Tangent, yes. What the heck. All right, so I have an example. But I don't have a calculator. So you may have to get a calculator out. Blade angle is 20 degrees at station 30. All right, how do I know what the blade angle is? Anybody?
You can measure it.
I measured it. Used a protractor. I'll show you how to do that. Not right now. So I used a protractor. I said, oh, okay, it's station 30. Why did I pick station 30?
That's the 75%.
Thank you. It's a 75% station. So let's see. If I had a prop, if I had an 80-inch prop, what does that mean?
The second half, 75 to the second half.
Diameter. So the diameter prop from tip to tip, it's 80 inches. Okay, so 80-inch prop. So I want to know what the 75% station is. So what do? Do I multiply 80 times 75? Nope.
Divide by two.
Okay, 80 divided by 2 equals 40 times, I hope this works out, 0.75 equals,
30.
does it?
Man.
Woohoo! I was nervous there for a minute. Okay, so I want to know what the geometric pitch is. Now, so what I've done is I said, okay, I've taken a protractor, and by the way, I could even do this on my plane or anybody's plane as long as it's a fixed pitch, proper, ground adjustable. It's not constant speed because that doesn't work. And I said, okay, I could go out to the ramp and say, hey, I wonder what this is. So I take my prop protractor, and first I have to establish a zero reference line, which we talked about yesterday, which is the crankshaft or something in line, plane of rotation. And I could figure out the angle at the 75% station. So all I need is a protractor and a tape measure, right? And I could run out there and I could measure it, divide by 2, figure out 75% station, measure out 30 inches, put a protractor on there, figure it out that it's 20 degrees, and run away, right? Now from here on out, I could figure out the geometric pitch of this because I don't want to get caught out there, you know. So geometric pitch equals, okay, so we're looking up here, 2 pi. And so what is 2 pi? We'll just put 2 pi. 2 pi. I want some pi now. 2 pi times, what's the R? Uh-oh.
No, it's 2 times R, which is equal to the diameter, right?
R is my, uh-oh.
R is 40.
R, that should be radius, but that doesn't work out that way. Hang on, R. Uh-oh. Take a break.